Hello everyone. So today we are going to do something a little more advanced. Although I say that this is whole exercise I'm doing is in the spirit of doing preparation for uh, MCAT and JEE, but I think today is probably not necessary to do in the MCAT, but the JEE is sometimes you do need that, okay, for the engineering schools. So it's a kind of preliminary to the more advanced mechanics of rotation. So I do say it's advanced, but advanced for introductory, okay? And probably mostly I'm going to talk about concepts before I do problems, because the problems in this domain are not accessible unless you're thinking properly, proper mathematical framework, okay? Proper mathematical framework is thinking in terms of vector, uh, like if you rotational velocity, like you've used letter omega, and this is scalar thing, but we would want to have think this as a vector quantity, and it's kind of not easy to think what is, something is rotating like or going around like that, and vector is straight, so vector is going to be straight and something's rotating. How does that become straight, So that's a problem. And related is once you get how to get from scalar to rotational velocity, that's going to be like vector like that. So once you get from this to this, when you go to this, you probably solve a whole bunch of problems. But because once you understand that, you get a pretty good take on how to think of angular momentum as a vector. So we talked about L, and we talked about I, omega, like this moment inertia, this is omega. But this is actually a very limited picture, and I know in MCAT you can just skip over these details, and there's only one I that will be relevant, and one omega that will be relevant, and one L that will be relevant. So you don't need to make a choice between what's relevant in a problem and which part is not relevant. But when you get a little bit more advanced problems, you are going to have to think of this as a little expanded view that L is a vector. So this is a vector, then what is that? So you over here you can think of that x components as omega x, omega y, and omega z. So then how do you combine this and make a vector out of that? That turns out to be a little more complicated, and that involved thinking of this guy as 9 components. Like this guy has three components in general in 3 dimension. So the vector has 3 components. This guy has 3 components. Omega itself just one, scalar. But so this I, when you replace this with some new I, some bold I, and omega, then this 3, then this guy turns out to be 9 components. So pretty soon it is getting very complex, right? So this is, we say it's a tensor. The vectors have 3 components, and this tensor, which has 9 components. And this is actually something called 2 tensor. The vector is, in this language, like a vector is 1 tensor, and moment of inertia is 2 tensor. And then there, of course, you can say there are things which are more than this, that can be 3 tensor, 4 tensor. So what are these 1, 2, and 3? They say how many index you need to specify it. So over here you need index, just one index. Let's in general you can just say, hey, I need to have a little better language. So I'm going to just say omega I, and say I can take x or y or z, or you can just say I is 1 for x, 2 for y, 3 for z. So you can say vector will have, can be written as component form that way. So there's only one index needed. So that's the one. So if I have a 2 tensor, it's going to be like a, say this guy, we're talking moment of inertia, then you'll have some I and j, and I goes from 1 to 3, and j goes from 1, 2, and 3, independently what the y is. So that's, you can say 3 times 3, so that means 3 times 3, that means 9 components. And that's where the 9 comes from moment of inertia. And we'll see how that comes, okay? I'm going to build up in several mini snippets of videos. So this is like a first of the several of these. So right now we want to focus on getting the rotational velocity, and understanding that, and then we can take it from there. Okay, so let's look at a really, really simple example. So and then from there we can say build up. Okay, so here is an example like this. So I've got the x-axis and the y-axis and the z-axis. So this is positive directions, and we can say that some the point mass is in the xy plane. In the xy plane. So this is xy plane, and this is just a single point mass. Okay, point mass m, and there's nothing more. Okay, just at one point. So it's moving. So you can see that it's going in, say at time t is over here, and a little bit later time t plus delta t is over here. So if you look at how much distance it has covered, say this is going in a circle of radius r. So the distance it cover is delta s. So delta s, so from t to t plus delta t, delta s covered, distance covered is r times this delta theta, right? And so if I divide by time, this delta theta, divide by time, and I take a limit, and so I take a limit delta t goes to 0, both sides. So this is what the speed will be, and this is r omega or omega r, whichever we want. I prefer writing like that. It will become clear why I write that way. V equals to omega r. Okay, so that's where the scalar thing comes from. So this all is scalar. If you wanted to write this as a vector, I can do that, but it's really not very helpful, but just become unnecessarily complicated. So the way we think of this vector, we say omega is along perpendicular to the circle it's going in. So this is z-axis. So if the motion is in this plane, If it's rotating in this plane, then omega is up there. And the position vector, this is origin, this is the position vector r of t is, so r of t is pointed along, let's see, along this direction. So this is x and this is y, and that direction is a polar radial direction, which is so, and has a magnitude r and polar radial direction. Now at a little bit later time, the polar direction is this way at time t, and polar radial direction and this time is t plus delta t. So that's the one actually time dependent, and this is constant. So what this is, in terms of v is pointed tangentially. So the v vector, velocity vector, is some speed, okay, some speed, and is pointed e hat theta, and sometimes this guy I write e hat radial, okay. This one sometimes just, this one can be simply just written at theta hat direction. This is unit vector. So this is also depends on time, and this can also depend on time, speed, if the speed is changing. So the v is like that. And so if you look at omega, will be some omega k hat, and r will be r rho hat. So, and the v is v theta hat. So if you know that k hat cross rho hat is k hat, this cross this is actually going to give you theta hat. These are unit vectors. You can actually check it. Like a rho hat is going to be cosine theta I hat plus sine theta j hat. Is from before we've talked about polar coordinates, and theta hat is going to be theta hat will be minus sine theta I hat plus cosine theta j hat. You can see if you take a dot product of this with this, you should get 0, okay, and k hat is k hat. So using this you can check that. So now put all this together, and this knowledge, you can see the v is omega cross r, and this is going to be very fundamental information, okay. This is going to be fundamental formula. So this is in a simple setting. Let's do a little bit more complex setting. It looks like some noise kicked in the background, so I am going to stop this and stop that noise and then come back. Okay, so I was able to turn off the noise. So another example which is kind of like a simple but not this simple, this was too simple, okay. Let's do this example. So now I have x and y and z, but this time still going around the z axis, and still radius is still r, And so it's sometime it's at t is here, some other time it's over here. So this is t, and at that point it's t plus delta t. So from here to here is that's r of t, and from here to here distance is capital R, and this is some fixed point, let's call it a, z equals to a point. So you can see that this if you do a vector here, so at time t you can see the relationship r of t equals to a k hat plus r, the radius, and rho hat. So if you look at the projection of this thing over here, that direction is rho hat, and this much angle is theta. Okay, so that at time t plus delta t, this have rotated, and so this at time t, and r of t plus delta t this will remain the same, plus r will remain the same, but rho hat will be in a slightly different direction. Is going to be in that direction. That will be rho hat at t plus delta t. So if you want to know the velocity, so of course you know the velocity is in that way. So velocity is in the, so you from here you already know the velocity should be in the direction of theta hat, right? But let's see, we work it out, and that should be the answer. So let's look at rho of t is cosine theta I hat plus sine theta j hat, and rho t plus delta t is cosine theta plus delta t I hat on delta theta t plus theta plus delta theta plus sine theta plus delta theta j hat. Now delta, we're looking at a small delta theta, so we expand this as a cosine theta cosine delta theta minus sine theta sine delta theta I hat, and this guy will similarly go into sine theta cosine delta theta plus cosine theta sine delta theta delta theta delta theta delta theta j hat. All right, now for delta theta very small, up to linear order, so this will just be 1 minus delta theta square over 2, and sine theta will be just delta theta. So if you expand it, this will be the this guy and this guy will be the dominant, this will be the subdominant, and this part can be ignored. So this relates to cosine theta minus delta theta sine theta I hat plus sine theta plus cosine theta delta theta j hat. Now when you subtract this to get a v, So when you do V, vector will be r at t plus delta t minus r at t divided by delta t, and then you take a limit delta t goes to 0. That's going to be very simple. It's just going to only these guys will survive. This a's will cancel out, and have r times delta theta times minus sine theta I hat plus cosine theta j hat, and this is what the theta hat is. So this is r delta theta hat, as we expect. All right. Now let's look at what r is. So you know r, if you look, we just over here, from here I know that I can write this in vector r rho hat equal to minus a hat plus r at time t minus a k hat. So this r may be coming from there, and if I say delta theta, I didn't divide by delta t. So this omega, if we say omega is equal to this delta theta delta t, and the axis of rotation is k, is still axis of rotation is k hat. So once again we see that this guy, and we say k hat cross rho hat is theta hat. So how do we get how do we replace this by the appropriate quantities? So this is going to be, if I replace this with omega k hat cross r rho hat, this will give me the same answer as that, writing that for omega. Now this thing can be replaced with this, because if you have omega k hat cross a k hat, that will be 0. So I can just replace this guy with that in this formula. So omega k hat cross r. So the V is omega cross r once again, right? So this is a very general, and I could have, rather than using this example, I could have done really general thing where next example, if you want to work it out, say this is some arbitrary direction, and something is rotating around here in arbitrary direction, so some direction, say n hat, which then that direction you have to specify that direction, and this time omega will be not just omega z but omega x I hat plus omega y j hat plus omega z k hat. It's going to turn out something like this, or will be omega n hat. So writing omega n, if you write n hat with I hat j hat k hat, you'll have 3 different components of omega, and if you work it out, at some instant you got the velocity vector perpendicular to that in this plane. So velocity vector is that way, and r vector that way, and n vector, omega vector is that way. So if you work it out, you find that once again you can get omega cross r, this r from the origin to wherever it is at time t. Okay, so this is a really an important formula to remember, and it will give you the velocity direction given the omega direction and where the particle is at that instant in time. Okay. Next, what we need to do is to look at how the angular momentum and other quantities actually get affected by this way of thinking. Okay. So maybe I'll add it to this video, or maybe new video for that. So see you next time. Bye.